Hello everyone, I'm George. You may know me from yesterday or any other Lambda Jam that's ever happened. So this talk is entitled Comma Police. I couldn't resist the Radiohead pun, but it was either going to be that or Comma Chameleon. But your reaction just told me I picked the right one. All right, so we've got all this data. It's in all these data formats. These ones, right? And probably some others, but we've got all this data, right? And where did we put it? We put it in text. And that's where these data formats come in. We've got all this data in text, in formats, and we need to deal with it because text isn't very useful. We need to get good stuff out of there in order to be able to do cool things, make lots of money. So this is the problem. I've written a library called SV for doing separated values, often separated by commas, not necessarily. They could be separated by your favorite Unicode character, so comma, pipe, poo emoji, whatever you'd like. And I'm going to talk about a whole bunch of things that I think are very good about it, that I'd like to see in other libraries or that people could improve again. And I'll tell you about some bad things about it that you can avoid. So hopefully you'll pick up some extra tricks to use in your library or to use to help you choose which libraries to use. Like you think, oh, George had a really good idea with that. I'm going to look for that in a library. Or like, George is crazy. I'm going to avoid anything like his rubbish. But either way, I win. So it's CSV. It's very popular for data science. Everyone's doing that, I think. And there's this document called RFC 4180. So I think what happened here is a bunch of Fortran programmers started putting commas between text, and they all did it very slightly differently in a sort of Tower of Babel kind of thing. And then they said, oh no, all our comma-separated values are a little bit different. Let's write a document to standardize on, and then they won't be. So they wrote a document to standardize on, and all the comma-separated values are still a little bit different. So the general structure of a library for handling one of these data formats is there's text, and then we parse the text, and in the middle we get this intermediate CSV data structure. So this is kind of like a syntax tree for the CSV format. And then from there we do what I call decoding. So we pull out, we pull out these domain-specific user data types that we define that we're actually interested in. Okay, and so I will try to be very consistent with my vocabulary of parsing and decoding. And drinking water. And then we need to go the other way as well. So we have our data types and we need a CSV out of them. So we encode to a CSV data structure and then we print that data structure to text. This is one way we could design a library in very broad strokes. Or we could do this. We could skip the intermediate data structure altogether and just say parse and decode in one go, right? And then on the other side, just encode and print. So take my data types and make text happen, right? Without an intermediate data structure. Sorry. Anyway. So in SV, we chose the former method. We've got these very strict phases that are separated from each other. We parse, we decode, we encode, we print. So we do have an intermediate data structure. Okay, and there are benefits to both sides. There's a bunch of stuff we lose out on. Oh dear. All right. So for example, if you just go directly from text to data types without an intermediate CSV representation, you're obviously not going to allocate an intermediate CSV representation. So you save on memory usage, and allocating memory takes time, so you save on time. It's much easier to do streaming with an approach like this. But we get some really interesting opportunities that come up if we do make an intermediate data structure, and in particular if we make a very pedantic one. So I think we have the potential to do better errors. You could do good errors with the direct approach as well, I think, but I haven't explored that very much. If you've got this intermediate structure that's keeping around all this information from parsing, you can make all these decisions based on that structure that would otherwise kind of be thrown away. And you can manipulate the intermediate structure itself and then just print that thing back out without even going to data types. So I'm going to elaborate on all of these things throughout the talk, and hopefully you'll find them cool. So here's a different workflow, in this case where, this is what I just alluded to. So we start with text, we parse it into a CSV data structure, and then we just manipulate the CSV data structure itself directly. We don't need to extract out types of like our stuff. We can just manipulate the CSV itself and then print that back out. So here's a CSV document, and this one's pretty atrocious. It's got some single quotes for quoting things. It's got some double quotes for quoting things. Some things are unquoted. It's like it's a total mess of quotes and needs to be sorted out immediately. So here's the code to fix that. Don't worry about the details, but in broad strokes, I'll tell you what it says. This uses traversals from the lens library to say, target every position where there could be a quote in the document, and then this function fixQuote says, where there could be a quote, make sure there's a double quote there. Okay, and because we've composed these traversals to target every quote in the document, we just say, run this function that fixes the quotes. Every quote in the document gets fixed. So we turn this, a horrible one, into this. We've got all these quotes, and they're all double quotes. But what's really important about this process that you might have missed is there's a space after the comma, after George, all right? And in the process of fixing all the quotes, we have not messed up the spacing. You can't see it, but these are carriage return line feed new line terminated lines. And they are still, in both of these documents, carriage return line feed. Okay, so when I fix all my quotes, I don't want to clobber everything else about the document. So our intermediate data structure is really pedantic about keeping quoting information, spacing information, new line information, right? Then you can write these functions that fix every quote, and everything else is the same. So you can use this to write these custom sort of sanitization programs or these custom CSV linters. You can go through and ask the question, is every quote a double quote? You can, you don't have to just change quotes. You can say, I hate carriage return line feed. Let's do line feed all the way, baby, right? You can do that. I think there are a lot of people out there doing data science, not at Lambda Jam, and they're doing it like with Python or R or Julia because they've got these really mature ecosystems full of tools, right, that Haskell doesn't have or has in some form. But like, I can't get up here in 25 minutes and convince them to use Haskell for their data science just yet, right? I think in a few years, hopefully we will. But what I can do is say, look, you've got your Python data pipeline or whatever, and you're calling like, I don't know, like my Python library .parse, and then CSV turns into stuff, and then hopefully it's good, right? What you could do is use my library to define a really strict set of CSV linters and sanitization tools, put that at the front, keep your existing data pipeline, but for the actual data cleaning bit before the interesting stuff happens, you've got this boring data cleaning job, do that in Haskell, and then pass it to the same pipeline you're already using. I think there's a big opportunity there that I hope people will use this for. So that's why I have this intermediate data structure in the middle, and that's why it keeps all information like quotes and new lines and spaces. But that's not the main reason people would use a Haskell library for CSV. They would use it to decode. So they would say, all right, parse the text, give me the CSV data structure, now decode, get types out of there, right? Like real types, like types that I care about that I can use. So I want to show you what that looks like in SV. We've got a data type for decoders. It's called decode. It has two type parameters, S and A. S is the string type, which is usually byte string, that we're decoding from, and A is the thing we're decoding to. Sorry, I'm a bit sick. So we've got all these primitive decoders. Goodness me. We've got all these primitive decoders, and now we need ways to stitch them together. We will stitch them together using functor, applicative, and alt. Alt is nearly alternative. If you know what alternative is, pretend it says that. So we've got these primitives and combinators, and we stitch together decoders that way. Let's see what it looks like. So here's our CSV from before, after we fixed all the quotes. We didn't really need to, but we did. We've got persons, they have names and ages. It's the best example in the world, and I use it every year. I'm going to use a better one next time. So a person has a name and an age, text and int. We write a decoder by getting the text, then getting the int, calling the person constructor, and using applicative to stitch it all together. Here's another CSV file. You've probably seen ones like this out in the wild where we've got just variable numbers of columns. So, so some people have a first name and a last name and then an age, but have you seen the article of like all these nonsense things programmers believe about names? So some people just have one name, right? And some people have, one really long name, or they've got two names in separate fields, or they may even just have like two names in one field with a space. It's CSV, we do whatever we want. So we can make a data type that says, well, maybe a person has one name, or they have two names in this document. And then we can use this applicative style here to say, well, look for a text and then an int, but if that's not what you find, instead look for two texts and then an int. And that's what this combinator over here is doing with the exclamation mark in it. And then we can get a person out, whether they've got one or two names. So I really like this applicative style of composition of decoders. Decode is also a profunctor. So if you went to my talk last year at Lambda Jam, you know what a profunctor is. Decode is one of those. All right? And you'll say, well, what's the benefit we get out of it being profunctor? So if we've got a decoder that takes a byte string and turns it into an A, but we don't have a byte string, we've got a text, right? If you're a Haskell programmer, you've been traumatized by different string types all over the shop, doing all these crazy different things. But we know how to turn a text into a byte string. So what we do is we use diemap from profunctor to map over the input with this function to say, get the byte string, get the text, turn it into a byte string, feed that to the other decoder. Now this whole thing is a decoder that works on text. So a lot of other libraries use type classes for this. So they don't have I've got an applicative combinator style but a lot of libraries are using a type class for this. So you might ask, why not a type class? Well, a decoder is something that I want to manipulate. I want to build a few primitives, some ways to manipulate them, some combinators. And also there are many different ways to decode the same thing. There are lots of ways that a Boolean could be encoded. A Boolean could be like a capital Y or a capital N, or it could be like a 1 or a 0, or like yes or no, or true or false, capital letters, lowercase letters. If I would use a type class-based approach, I would have to think of every way that anyone could ever encode a Boolean, or I would have to prescribe your Booleans look like this, and I didn't want to do that. So I just made it data types that you can build yourself and stitch together. Here's a good function. It's called ignore failure. And it says, given this decoder, try to run it on the column. If it fails, just return nothing in maybe. So don't stop the decoding process. Just keep going, but put nothing there. So here are some ints. Not actually. We've got 3, 4, 8.8, 1, and null. Null is everyone's favorite int. But if we use ignore failure, we can say, then we get back, just 3, just 4, nothing, just 1, nothing. So we just get nothing wherever it failed to get an int, basically. And this thing has the type decode SA to decode S, maybe A. If we were using a type class-based approach, this would be an excellent candidate for the maybe instance for that type class. But it's one of 3 combinators of that type in the library, and I didn't want to pick one. So we've got a bunch of different combinators with the same type with different semantics. And if I were to use a type class-based approach, I would often have to pick one of them and say, this is the blessed one. So I'm sort of vigorously defending my not type class-based approach here, because everyone else is using type classes for this nearly. But I love type classes so much. At Compose last year, I gave a talk about why type classes are the best thing in the universe. So I'm not against type classes, right? I think there are lots of things they're really useful for, and at this time, I'm leaning against using them for this task. So I want to be really clear about that, because type classes are the best thing in the universe. All right, so let's parse some more CSV. Now that we're getting good at it, you know, we've got to keep going. Here are some conferences. These are really good ones. So we've got, we had ComposeConf last year, and there'll be a ComposeConf this year. We had Lambda Jam last year. There'll be a Lambda Jam this year. Presumably this is a lot longer. I couldn't find like what date Lambda Jam was in 2014 or whatever, but you know, I could have put it in here. We've got this date format, and it's like YYYYMMDD. And we could just say string or whatever, but that's not cool. Strings are not cool. We're going to destroy them wherever we see them. Put something good there instead. So there's a library called data.time. It's a pun on time because time is a herb. And this gives us a year, month, day type. Okay? And so we can write a data type for our conference CSV rows that has a text for the name of the conference and then a year, month, day. Now, we can decode text pretty easily. We've done it on previous slides. But how are we going to decode a year, month, day? I don't know, but I do know how to parse one. So the time library gives us a parser written with the attoparsec parsing library for parsing a year, month, day, given a byte string. And in SV, we've got a way to build a decoder out of a parser from your favorite Haskell parsing library. So if you've got a parser for your data type, you can just get a decoder for it for free, which is pretty cool. So we'll do that. We'll call the attoparsec function from SV, and we'll turn that parser from the time library into a decoder, and now we can decode the conference CSV, which is pretty cool. Another thing SV does is SV uses error values, not error messages, error values. So this is an error value, or this is part of it. There's a bunch more constructors. But we've got all these constructors that tell us what the error was. So unexpected end of row says, I needed there to be another column, but there wasn't. Expected end of row says, I thought the row would end here, but there are 3 more columns. So here's what they were. Right? And then we've got some really boring generic ones that say just bad parse or whatever, and that just is a string. But, and there's a bunch of other ones I don't want to fully explain. But the thing is, we've got this data type that describes what kind of error occurred, and then we can do something about it. So if you've got a string for an error, when an error happens, the only thing you can do is show the string to the user and say, here you go. I guess you could reverse the string or do whatever else, but you know, you probably wouldn't. But I can write a function that says, run this decoder, and if errors happen, call this function to build a new decoder and, you know, carry on or do whatever. Right? So we can look at errors, inspect what kind of errors have occurred, and do something depending on that. Whereas if our errors were a string, we would have to like put our errors in a string and then write a parser for our string that was our error message to figure out what kind of error occurred if we wanted to like recover from errors. We won't do that. We'll do this. And SV has error values, plural. So rather than using the famous either data type for errors, SV uses this data type called validation. And validation goes like this: data validation EA equals failure E or success A. And you'll say, George, that's just either. You're crazy. But I am, but it's not. So the difference between either and validation is in the applicative instance. So validation has an applicative instance with a semigroup constraint on E. And what it does is it uses that semigroup constraint to append your errors together. So if multiple errors happen, you get all of them. So we just get that decode error type from the previous slide, wrap it in a non-empty list, which is a semigroup, and now we can run all our decoders, multiple ones can fail, and we get back all the errors that occurred. Has this ever happened to you? You're typing away, doing something, maybe you're writing a program, maybe something else, you're typing away and you hit go. And the computer says, sorry, there was an error on line 56. And you say, oh, that's fine. I've made a mistake, silly me, thanks computer. All right, 56, oh, there's the problem, fix it, all right. Go! Sorry, there was an error on line 57. Oh, okay, all right, fix line 57, there we go, all right. Go! Right. Sorry, line 58, oh, error, right? That's so not cool, you can't iterate that way. You like fix one thing and then another thing pops up. Just like you could have told me all 3 lines had errors on them and then I would have fixed them in once and I wouldn't have had to press the button again. And that's what I'm going for here. So now let's have a really bad attempt at parsing something so I can demonstrate how good my errors are. Here are 3 strings. Let's parse them as 2 ints. So we'll write our decoder by getting the int decoder and using it twice and using applicative to put it in the to constructor. Okay, and now let's parse that file, see what happens. Errors happen, but in a good way. So this says, right, I couldn't parse the string A as an int, that was a bad decode. I couldn't parse the string B as an int, that was a bad decode. And I hit an unexpected end of row. There were too many fields. There was 1 too many fields and its contents was C. That's everything wrong with our attempt to parse that file, or to decode that file rather. And some of it is too stringy for my liking, but it's a lot better than, you know, a lot of other things. And I'm pretty happy with that. And I could handle this, so I could say, well, if there are bad decodes, I can't do a lot about that. But maybe if I only had the unexpected end of row problem, I could handle it in some other way. So I'm pretty happy with that as an error. And you'll say, all right, well, that's decoding. That's one direction. What about if I've got all my Haskell data types and I need to make CSV out of them? Well, for that, I would use encoding. I would encode to a CSV data structure, and then I would print the data structure to text. Printing the data structure to text is pretty boring, and I don't have much to say about it. But I will tell you all about encoding. So we've got a data type for encoding like we do with decoding. Decoding was an applicative, and I assume you were all at my talk yesterday, and so you won't be surprised that, oh, I have these primitives as well. You won't be surprised that encoding is a contravariant functor that's divisible and decidable. So if you went to my talk yesterday on divisible and decidable functors and you came out of it thinking, oh, that was full of lots of nonsense made up toy examples, I've used it in my CSV library, and you can go and look at that. And that's really helpful because I don't have time to explain those type classes now. All right, but we use contravariant, divisible, and decidable to compose together our encoders to split up our data type and then, you know, put it into columns effectively. And we've got semigroup as well, and that's helpful. We've got all these primitives. They'd be the ones you'd expect, so like put an int there or whatever. A really interesting one is encode of, which says, given a prism from S to A, so like if an S might be an A, and you know how to encode an A, I'll tell you how to encode an S, right? In fact, it's much more general than that, and it doesn't have to be a prism. It has to be like a getting SA or something. So it works with lots of optics. But what you can do is you can, like, if you came out of my talk yesterday and thought, well, divisible and decidable are rubbish, I hate them for some reason, then you'd be able to use this and not have to use those combinators. Then you'd be able to, like, say you already have all these prisms lying around for your sum type, you could just use encode of with all your prisms and semigroup them all together. It would be very cool. So we've got encoding, and it's a divisible, decidable, contravariant functor. And it works pretty well, and I'm pretty happy about it. So everyone in the audience, right, or at least like I think a lot of you, I've been talking about all these cool features and like, oh, I've got more errors than you or whatever. And you're like, I don't care. Nothing you've said so far matters, George. You've got a CSV library, right? Is it fast? That's the only thing that matters. I don't care if it like works or is useful for anything else. Is it fast? Preferably blazing fast. And I've got an answer for you. No. So I've done some benchmarks. So this library is only like, I've just put up the first version recently, and then I haven't had time to fix any of the problems with it because I've been writing talks about it. But I did do some benchmarks. Like I was happy to release something that was dog slow as long as I know just how horribly slow it is. So I did some benchmarks. I used Hedgehog to generate a 100,000 line CSV file. It's got texts and ints and doubles and product types and sum types. So it's not just like just a big block of text, right? I think like it wouldn't be very good if I just benchmarked based on like getting text out of CSVs. So I've got all these different data types. And I benchmarked SVs against Cassava, which is kind of the dominant Haskell library at the moment and is, oh, they're a Wi-Fi, cool. And Cassava is kind of the thing everyone's using. So if I'm going to benchmark, I'd better compare myself to Cassava or no one will care. SV's parser is actually polymorphic in parser combinator library. So if you like trifecta, you can use trifecta. Or if you like parsec, you can use parsec. I instantiated attoparsec because it gives me the best results on the benchmark. So here's our benchmark. Blue is SV and red is Cassava. Lower is better. If you parse and decode your CSV using SV, we're like 4.5 times slower, which is really atrocious. It's like 4.5 seconds instead of less than 1. But remembering the beginning of the talk, I chose to really fiercely separate the sections. We parse and then we decode. We don't like parse and decode all mingled into one thing. So I can separate it out. I can say, well, how good's my parser and how good's my decoding? And it turns out my decoding is like pretty much more or less the same speed as Cassava. And my parser is terrible. Right? So I'm going to go home from LanderJam and probably take a day off tomorrow because I'm pretty sick. But after that, I'll work on fixing up the performance of my parser. In the meantime, just use my package SV Cassava that gets Cassava's fast parser, puts on SV's decoding, and then it's pretty fast. So that's probably the biggest benefit I've had out of my decision to like strictly separate these phases is if one of them's really rubbish, I can just borrow someone else's. So I've spent most of the talk talking about how good the library is. With the benchmarking I've shown you, it's like not perfect. So I've got one slide to cover the rest of it just really quickly about how bad it is. We can't decode based on column names. It's all positional, like the third column is a string and the fourth column is an int. But nobody wants to write that way. Everyone wants to say, there's a column named average and it's a double. Or there's a column named name and it's a string, right? And then stitch these things together. They don't want to use positional. Like, oh, I have to remember the third one. Is that the average or the max? I don't know. We can't do that yet. I think I know how to do it, so I'm going to try and do that. I told you about how great all my errors were, but they don't actually tell you what line they're from. So I gave this example of like, oh, line 56, you've got an error. And I said, oh, my stuff's way better because we give you 3 errors. But they don't tell you what lines they're on. So that really needs to be sorted out. We don't have any form of streaming. So if your CSV is like 5 gigabytes, then don't use this library yet. And as you've seen on the previous slide, performance needs work in a bunch of areas really, but in particular in parsing. So there are a whole bunch of limitations that mean you might not want to use this now. You might want to, I don't know. But I couldn't just get up and give a talk about my like horribly slow library with a bunch of missing features that everyone cares about and not mention all these things. So there they are in one slide, brushed past really quickly. Maybe you'd like to help me with some of those things. So you can come and put a pull request into SV if you want. Otherwise, I'll keep working on it, so don't feel too stressed. But if you're like way better than I am at Haskell, then please do come and help. Or if you have like this crazy CSV with all these different line endings and all these different single quotes and nonsense, and my separator is the ASCII poo emoji, or the Unicode rather, then send me your CSV file and say, hey, can SV do this? And maybe it can't, and I'll change the library and fix it. So you can talk to me about all that stuff. I have some references, and that's the end of the talk.